Hello, last little video for tonight, ignore that. One or two people have asked me for a little bit of help with the mock, so I'm going to go through how to do just a couple of questions. This is a question near the back end, I think it's question 32, DI and DII, and there's a DII I'm going to cover as well. So this question people found tricky, so I've just worked it through, checked I've got the right answer, and happily I have, so that's good news, and hopefully I'll be able to help you with it. You're told you've got a solution of this weak acid, methanoic acid, and it was neutralised using sodium hydroxide, and asked to work out the mass of the methanoic acid there was in the first place. So this is chemistry, so you've got to work out what chemistry is going on in this titration, and really then you've got to know what the reaction is between methanoic acid and sodium hydroxide, and written that there's methanoic acid, where this is, just remind you that methanoic acid is a carboxylic acid, which is that, it's got one carbon, and I'm just going to call it as HCOOH. That's how we write that's how we write carboxylic acid, isn't it? This is the acidic hydrogen, which is this one here. That reacts with, we're told it's monobasic acid, or monoprotic acid is what I would call it. With sodium hydroxide wants to give sodium methanoate. You're told the formula of that there, and of course it's a neutralisation, you're going to get water. And so you can fill in, just like we've done loads of times with titration, to fill in what you know. So you're told you've got 25 centimetres cubed of that stuff, 20.7 centimetres cubed of that stuff, and it's 0.1 mole per litre concentration. So let's see what we can do. So there's the volumes, there's the concentration that we know. If we know the volume and concentration of something, we can work out the number of moles by doing that times that divided by 1,000, because this is in centimetres cubed, right? Just remember that N is equal to C times V over 1,000, and it's only divided by 1,000 because the volume is in centimetres cubed. This is in moles per decimetre cubed. If we know the number of moles of sodium hydroxide, we can work out the number of moles of methanoic acid, because in the titration they're going to react in a one-to-one way at the equivalence point. There we are. So that's the number of moles of methanoic acid there were in the 25 centimetre cubed sample, or aliquot. Okay, and I've written that underneath. So number of moles, this is how you'd write it in the exam. You don't need to write the table in the exam if it doesn't suit you, but the number of moles of methanoic acid in 25 centimetre cubed aliquot is this much, that number there. And you then would have to work out how much there was in your stock solution, which was a 2 litre stock solution. So they made a big old stock solution, 2 decimetres cubed, 2 litres, and then they took just 25 of that. How many times does 25 go into 2,000? Well, it's 80. So the number of moles in 2 decimetres cubed, which is 2,000 centimetres cubed, is that number times 80, which is that number. And you can work out, if you know the number of moles of something, you can work out the mass of it multiplying by the MR. Mass equals MR times moles, remember, times MR. And the MR I worked out earlier is 46, so because it's got 1 carbon, 2 hydrogens and 2 oxygens, 46. And so the mass in that 2 litre sample was 4.6176. And the next question is really similar to what we've been doing in class lately. So it's a question on pHs of methanoic acid. So just to remind you, I'm not going to do the derivation now, we've done that in class recently, but we can work out the hydrogen ion concentration of an unknown, without knowing the pH, we can work out the pH if we know the hydrogen ion concentration, and we can work that out if we've got the Ka and the concentration of the weak acid. Right? So the Ka is given to us in the question, at least the pKa is, and we can work out the Ka from that by doing 10 to the minus that value. So that's the Ka of the weak acid. And how do you work out the concentration of that? Well, you've just worked out the number of moles of it in the previous question. That's how many moles there were in 2 decimetres cubed. So we can work out the concentration by doing concentration is equal to the number of moles divided by the volume. Right? We know that's moles per decimetre cubed, moles per decimetre cubed, moles divided by decimetres cubed. And so that comes to 0.0828 moles per decimetre cubed. I plugged that number, which is that number, and that number, which is that number, into this equation, did the square root, and I got the hydrogen ion concentration to be that. So that's the hydrogen ion concentration. Works out the pH by doing minus the log of that number. It comes to 2.42, which feels about right for a weak acid. And I checked the answer, and that's exactly what it says in the mark scheme. Right. So, anything else on that one? No, the second question was, oh yes, it was this I was going to mention as well. So the following question, which I wasn't asked for help with, but it is what we've literally just done in class. Would the pH of the salt, the sodium methanoate, be greater than or less than 7? So remember, there's two ways of thinking about it. It comes from sodium hydroxide, strong alkali, and methanoic acid, weak acid. The tug of war analogy. So the tug of war analogy says that the salt made from a strong alkali and a weak acid would be slightly alkaline. So we can say pH is going to be greater than, the pH is going to be greater than 7. So we're going to get a mark for that. I imagine I haven't checked the mark scheme on this one. The explanation for that is showing that the methanoate ion, which is this stuff, will react with water. Yes, there's an equilibrium, but importantly, it will generate the hydroxide ion. I don't know whether you need to write an equilibrium sign. I'm just going to check the mark scheme quickly. Pause this. Yeah, it accepts it as an equilibrium sign. That's the preferred answer, but it also accepts it as arrows, and that's fine. You can explain it in a bunch of other ways, which is, it says, well, you've got the mark scheme, haven't you? You don't need to read that to you. The next question was around a redox titration. People always find redox titrations difficult, but they're exactly the same as titrations, except usually the ratios are different and you don't need an indicator. You don't need an indicator because the permanganate, which is purple, changes colour when the reaction takes place. This is very strong purple colour, this is pale pink colour. Everything else is just the same as any other titration. You're told, so summarising the story here, we've got some spinach in a bag. Spinach has got iron 2 in it. You do a titration every day for a few days to see how the iron content disappears, using a known a stock solution of potassium permanganate. A little reminder, you need to know how to form stock solutions. If you've forgotten that from year 12, go figure it out again. Do I have some notes? I think I made some notes on this. Where are they? Oh, I can't find them. I'll just do it again. Oh yes, that's right. The first question was around, here's the data. It was comment on the uncertainty given in the data. Look how the concentration, the content of iron decreases over time, as you might expect from the clue of the question. And it says the uncertainty is plus or minus 0.05. This is right for each reading, the initial and final. No, that's not initial and final, so none of them are right. When you do a titration, each reading, the initial reading and the final reading are each plus or minus 0.05, remember, and that's plus or minus 0.05. There's two readings we do a titration: initial volume, final volume. Now, when you get a titer value, you have to add together the absolute uncertainties, the absolute uncertainty for the initial reading and the final reading, and so this is incorrect to use those values, and so the uncertainty should be 2 times that, which is plus or minus 0.10. So you get a mark for saying they were wrong to use 0.05, and they should have used 0.10. Okay. The question here was calculate. What are those? I've got the answers here somewhere. Right, so you've asked to work out what the percentage content of the iron was in the original, on day 1, in the original sample. We've got volume, titer volume, which is volume of permanganate, MnO4 minus, or KMnO4 if you like, which is 3.38 centimeters cubed. You're told in the question the concentration of permanganate, which was, I think it was 0.01. Somewhere it says that on this bit of paper, 0.01 mole per litre. So it gives it as capital M, which is the same, by the way, as moles decimeter cubed. There's the molarity, which is the same as that. So just like with any calculation, work out the number of moles of potassium permanganate. You can set this out as the grid if you prefer, which is what I've taught you to do. It works absolutely fine. You do the volume times the concentration divided by 1000, gives you the number of moles of permanganate is equal to 3.38 times 10 to the minus 5 moles. Go back to the balanced equation. You'll see that it's a 5-to-1 ratio. However much permanganate there was in the titration, there must be 5 times as much iron. So number of moles of iron is that number times 5. When I did that, I got, probably rounded this a little bit, but 1.69 times 10 to the minus 4 moles in our sample. And if we know the number of moles, dead easy then to work out the mass, isn't it, of iron by timesing by the formula mass. The relative atomic mass, which is for iron, is 55.85, which I'm sure you've got printed in your memory, times 1.69 times 10 to the minus 4. I've ended up there with, I rounded to 9.439 times 10 to the minus 3 grams. So that's the formula mass of iron times the moles, gives you the mass. But you're asked to work out the percentage, I think, percentage content of iron in the raw spinach. I can't see it, sorry. There you go. Percentage is, you've got that number, 9.439 times 10 to the minus 3, divided by 2.00 grams, which is what we started with, times 100, and that comes out, where does it say 2 grams? There's somewhere, there it is, 2 grams. That comes out at 0.472%, which is exactly what it says in the mark scheme. Happy days. Cheers.